All right, so like I said, good morning, good afternoon, good evening. Welcome to this week's edition of eoPERCS. My name is Elizabeth Seibert. I'm one of the organizers for this meeting, and today it is my great pleasure to welcome back Andy Fraass. Andy was actually a member of the initial eoPERCS committee and has since rotated off the committee, and we're welcoming him back as a committee talk. So today, Andy's going to talk to us about towards a more holistic understanding of microfossil records and evolution. So just a quick note for those of you who haven't been to a eoPERCS seminar before, the format of today's seminar. We're going to spend the first few minutes doing some welcome and announcements, and then Andy will give his talk. That'll be about 30 minutes. It'll be followed by a moderated Q&A period, and then a tea time after the talk, which is an informal chance to just hang out, chat, and think about fun science things. And as a reminder, eoPERCS does questions mostly via chat. So during the talk or after the talk, if you have questions, please send your questions via chat to the eoPERCS questions host. And I believe that person is Jana today, and they'll be renamed in a moment. Just a little bit of eoPERCS housekeeping is that eoPERCS values the participation of all people interested in paleosciences. And so we'd like to remind you to please abide by our code of conduct during today's seminar. We ask that you please stay muted for the duration of the seminar, even if you have managed to unmute yourself. Now is a good time to double check and unmute yourself for the duration of the talk. And as a reminder, you can ask questions via the chat to the questions at eoPERCS host. And we're also giving the opportunity to use the raise hand function at the end of the talk during the Q&A, if that is of interest to you as well. Any technical issues should also go to our questions host. Just a couple of other notes. We now have closed captions running built into Zoom. And so you can show or hide those subtitles by clicking on the CC button. And finally, we're going to drop a couple of links into the chat we always are on the lookout for excellent early career speakers. And so if you have a paleo friend you'd like to nominate, please go ahead and send us a nomination, and we'll drop a link to that in the chat. And then the other thing that we'll add is a link to our weekly feedback survey, which is just a chance to collect a little bit of demographic info, let us know who you are, and if there's anything we can do to continue improving these seminars. All right, so finally, we have a little bit of exciting news, which is that eoPERCS is now sponsored by the Royal Society of Chemistry and the Geological Society of London, both of whom are allowing us to expand a little bit and increase the diversity of the seminar series in a lot of really exciting ways. So we'd like to thank both the Geological Society and the Royal Society of Chemistry for helping to support early career researchers in paleo. And finally, now that I've blathered on a lot, let me bring us back to our today's speaker. So Andy Fraass got his bachelor's and master's from the University of Wisconsin before going on to do a PhD at the University of Massachusetts Amherst. He then held several different postdoctoral positions, including a Smithsonian Museum of Natural History fellowship, and I was a visiting assistant professor at Sam Houston State University, followed by a stint over the pond in the University of Bristol, where he was a research fellow for several years. And he has just started his assistant professorship at the University of Victoria in Canada. And so at this point, I'd like to invite Andy to take over the screen share and tell us all about all the epic things that you can do with microfossils.
All right. Thank you very much. Please share. All right, and hopefully everyone can see my screen. All right. I'm very happy to be giving this talk. This kind of feels a little bit like coming home. It's also the first time in 2 years that I've given a talk, so I apologize if there's any hesitation on my part. I feel a little rusty. Oh, that's not working. All right, hold on. There we go. All right, so having started a new position in Canada, one of the things that my new institution really values is it's developed a commitment to promoting Indigenous community and cultures and people. And so I am currently sitting in my office. And so I'd like to acknowledge and respect the Lekwungen people on whose traditional territory the University of Victoria stands. and the Songhees, Esquimalt, and Wasanich people whose historical relationship continue with the land to this day. It's nice to be in an institution that actually puts its money where its DEI mouth is. So I want to say that. So we're going to spend most of the time talking about the interactions between the biota and climate and the rocks that they form, and then the ocean. And that's, a very incredibly broad kind of discussion. And so I want to focus in on the particular feature of my research that's generally how do plankton respond to both biotic and abiotic forcing, and how does that change when you move between different background states, different climate states? So because I'm a micropaleontologist, right, all of us micropaleontologists start with a picture of the Zoides resolution because that's where we get most of our data. It's the founding, the thing that makes paleoceanography possible, right? So that's the Zoides. It goes out and it finds cores. It pulls them up from the bottom of the ocean. And if you're lucky, they look like that. So nice, clean mud. We've done this for about 50 years. So there's a tremendous amount of data. We've poked holes over a giant chunk of the world ocean. That's not to say that we don't need to do more. Of course, we need to do more, but we do have pretty good coverage. So if you're lucky, in my eyes, when you wash a sample, it comes out looking like that. You get nice white carbonate sediment. And if you sieve over a 63 micron sieve, then you end up with a bunch of forams that look like this. I wanted to zoom back out because I'm talking to a pretty broad audience. If you haven't taken paleobio in a long time and you're coming at this from, say, vertebrates, right? Planktic foraminifera are single-celled zooplankton. They exist from the late Jurassic to the recent. They produce a calcium carbonate test, which we think of as a shell. And the reason that they're so great for studying evolution is that we've used them for decades for other reasons. Right, oil and gas has used them to correlate and find oil and to find pay. We also use them for climate studies. And because we need to use their chemistry of their shells for understanding climate, right, we've got to understand where they're forming those shells. So we've worked out the ecology of this group fairly well. Also, because they're useful for other things again, right, we've spent a few decades recently standardizing the taxonomy as a community. And so all this different work for reasons besides studying evolution makes them really good for studying evolution. They're kind of a really good model system in which to do some really cool work. So of course, they're not the only game in town. There are 4 main marine microfossil groups. So there's also the radiolarians, which are siliceous tests, and they're sort of on the zooplankton side. And then there's 2 groups of phytoplankton. Those are the nanofossils, which tend to be calcareous, and the diatoms, which are siliceous. So what you're looking at here is an older figure, but it gets across an interesting idea, and that's the difference between ecological and evolutionary success, right? So diversity you could think of as like evolutionary success, and ecological success you could think of as abundance. And you can see that there are connections between these 4 different groups, right? And it's a cool thing to be able to take these several different ways of viewing these organisms and splitting out and investigating, like, are the carbonate ones working together in an ecological way, or are they're diversifying at the same time with evolutionary success? So the problem is we don't usually think about them this way. We usually think about them just the foraminifera or just the radiolaria, and we don't usually get this whole kind of group view. So I turn at the end of the talk to discuss why that is. But I also wanted to show this plot. So this is a map of the world ocean, the sediment that's at the top of the sediment column. So these, I'll actually use my mouse. So these down here are all biogenic sediments, right? And if we go back to like introductory paleobio, this sediment down here, right? These lines down here also, this is the disassemblage of marine microfossils. And so we're finding an enormous amount. So there's a tremendous potential to look at these things, not only from their evolution, but also in their sedimentary profile and how they generate sediment. So the problem with doing that, though, is that we lack a kind of shared framework that allows us to analyze the sedimentary and the biological data, the ecological or the evolutionary data all together. It doesn't exist right now. And so we're going to come back to that at the end after I think I've convinced you, hopefully, that it's a useful thing to do. So I wanted to start out with this so we can kind of orient ourselves. What you're looking at here is the macroevolutionary history, or the diversity column. I lost my mouse again. There we go. Of the planktic foraminifera. So we started out here in the late Jurassic. They diversify through the Cretaceous. They have a massive extinction at the end of the Cretaceous, diversify again through the Eocene, crash again through the Oligocene, and then diversify again into the modern. So one of the things that has been done looking at these groups is to look at the record and try to tease out what the forcing on the evolution, the diversification is. So Tom Hazard had a really nice paper in 2011 where he showed that if you consider the Cenozoic and look at the diversification pattern, their evolution is really controlled by the diversity dependence, so a biotic control, the climate, and then the ecology of the group. So there's a mixture of these different biotic and abiotic controls on the diversification. Now, that was an entire Cenozoic view, and it didn't have an analysis of the specific events and what might the events be driving in terms of the diversification. So we looked at the macroevolutionary rates. So here what you're looking at are the extinction rates. And everywhere sorry, I keep losing my mouse, where we have a really low extinction rate that we thought that was a significant extinction. So if we take these, right, and we've got several throughout the Cenozoic and the Mesozoic, we put them down here. So a significant extinction is in red, a significant origination is in blue. And then where we have these vertical lines, those are significant paleoceanographic events. And we're looking at also the genus level spindle diagrams. So what you see is that we have a good coherence or good correlation between a significant macroevolutionary event and a significant paleoceanographic event. So here's right. So here we've got the first growth of Antarctic ice. We've got the PETM right there. So there does seem to be this abiotic control on their evolution quite a bit. We also have this interval right here where there's, behind Shannon's head, there's a sign that says recovery, where it doesn't seem like there's a significant climate event, but there is a lot of evolutionary activity. So I was, at a meeting, and Chris Lowry and I were at a bar drinking and talking about science. And he brought up this paper that was from several years ago by Kirshner and Wheel. And we were talking about it. So in that paper, they suggested that it takes about 10 million years to recover from mass extinction. This was a very theoretical, lot of math kind of paper. And we said, okay, could we actually test this with real data? And of course, because it's Chris Lowry and I, we said, yeah, let's do it with forams. And so we did. So what you're looking at is one of the summary figure diagrams that we drew up for this paper. In Cretaceous, the planktic foraminifera are really big and they're really diverse. They're really flamboyant forms. As they go through the extinction, they all get really, really small and they get really, really simple, to the point where the bottom two on that figure look really similar to me. And I am supposed to specialize in these things. It takes about 10 million years before the disparity really increases to the same level as it was before the KPG. So we had a really good time with this paper. It was fun to do. Chris and I like working together, but really all it does is it takes that theoretical and crosses it out. It says, yeah, it does. Checked with real data. Done. This got picked up, just as an aside, it got picked up by the various national media. So we got written up in The Independent because we put in like an evocative phrase like there's a speed limit on evolution. We also got picked up by the Daily Mail, which means that I spent a day like looking through the comments, just trying to see what people were saying. And this was my favorite one. So apparently Chris and I are grant-hungry climate mixed scientists. So we decided that was an interesting idea, and we wanted to continue on with that kind of framework. And we started talking with Shelley Hull, who had been invited to give an annual reviews paper, and started thinking about the other microfossil groups. So we also brought in Paul Bowen and started thinking about this in a broader kind of way. And so this is a look at the diversification patterns for all the 4 main microfossil groups. And we basically showed in a more qualitative way that there is this kind of 10 million year recovery time after each of these big extinctions. The thing that really jumps out at me, though, when we were doing this paper, is that we don't construct our records the same way. So even between the planktic foraminifera, right? When I looked at the record and generated a diversity curve, we used morphospecies. Someone else, Tracy A, is doing work a little bit earlier, used lineages for the Cenozoic. So she removed the pseudo-extinction and pseudo-origination that happens when you have like a gradual transition from one species to the next. So even between one group, the records can be constructed very differently. You can end up with a pretty different curve. The same is true for nanofossils, for radiolarians, for diatoms. And so we don't really have a shared framework to do this kind of work in a really quantitative fashion. So there's some improvements that could be made within the group. So with that rattling around my head, I started talking to Ben Moon, who then brought in a master's student named Katie Jansen, who was interested in looking at high quality microfossil records. So we decided, well, Ben decided that it'd be really cool to use Pyrate, which is this Bayesian statistical technique for understanding macroevolutionary rates, but in a way that is sort of more rigorously statistical and allows us to look at a variety of preservation rates and uses a series of models to really understand where you get an important and key change. So Katie started out on the planktic foraminifera and then got apparently bored on a Friday night during the pandemic and downloaded the other 4 microfossil groups and tossed them into this Pyrate thing, ran them on the supercomputer at Bristol, and then came up with a really cool analysis that I don't want to really spoil because it should be coming out in paleontology hopefully pretty soon. But which on the right, she's compared all of the different microfossil groups and shown where there are similarities and differences between their evolutionary records. One of the things that really jumped out at me is that the planktic foraminifera record is much more boring than what we know from the literature, right? So there aren't too many features. And so this suggests that techniques like Pyrate are really good and they show the very important changes, but they're also missing some of the finer scale things, which perhaps is not that surprising, but still a useful kind of contribution. Katie, I think, is in the audience. And so if you've got questions about this, she'd be happy to answer them because I don't understand it as much as she does. So to summarize that, those bits, the patterns of evolution in the plankton are governed by a combination of biotic and abiotic factors at a million-year kind of scale, but it really depends on when we're talking. Sometimes it's the biotic factors, and sometimes it's more abiotic factors that are governing the way that they're evolving. So one of the things I'd be interested in investigating then is what happens on the sub-million-year timescale. So we're going to jump from talking about sort of macroevolution to talking about individual traits. And we're going to focus on size. So this is a cool Oligocene forum. I like Oligocene forums. And there's a big one and a small one. And so there are a variety of reasons that they could be larger or smaller. But then because these things are generating calcium carbonate, there could be consequences to them getting bigger or getting smaller. And so we're going to talk about both of these things. I am not the first person to do this, of course. There's a long history of doing it. And one of the people who's done it the best is Danny Schmidt. And she showed really nicely in 2004 that the main control on size for plankton foraminifera is temperature and possibly stratification, but that is linked very strongly with temperature. And so that's what this analysis is showing right here. So all of this work that I'm going to talk about is part of a NERC grant that was run through Southampton and Bristol and a few other institutions. And the main reason to do this work, the main thrust of the grant was looking at how developmental plasticity influences speciation. This was part of my postdoc and then fellowship. So the Bristol part of it had a variety of people, Danny Schmidt, another postdoc named Heather Birch, and then a variety of MSc students. And really what we were doing was providing the context for the people who are doing the fancy speciation stuff. And we were looking at what environmental conditions were driving changes in size. So I appreciate NERC for paying for me to move to Europe for 3 years. So we're going to be using a technique called automated microscopy, which is where we use a fancy automated microscope like you see in the bottom right, which zooms along and takes pictures. It analyzes about 2,000 individuals per sample, and we look at the 95th percentile of the test diameter. Now, this used to run really slowly, but now it runs quite a bit faster. We switched this over when I started my postdoc. So it runs about 70 to 100 samples a day until there's a pandemic, and then it runs 0 because no one's allowed to go in. So that happened in the middle of my postdoc, which was a shame. So the machine takes a picture, and then it uses some thresholds to remove things that aren't a foram. It does some automated detection of the maximum diameter, and then it plots up a histogram and gives you information like this. It's really bad at things that are less than 150 microns. So we've artificially truncated the histogram here by sieving the material physically. So this means the mean and the median aren't really a mean and median. And so we don't use those as a piece of information. So we instead use the 95th percentile of the size, which is more robust and more repeatable kind of measurements. So what you're looking at here is a lower resolution look from about 14 million years ago to the sort of recent. The red are the tropics, the subtropics are in orange, and then the green are the upwelling regions. So you can see, I think, is that about 6 million years ago, there's a pretty broad increase in size of about 150 to 200 microns in the mass accumulation rate of the plankton forams. The other thing that happens at the time is that the plankton forams tend to accumulate a little bit more. We also get a roughly constant mass accumulation rate of carbonate. So that's kind of a really interesting thing. We think that this has to do with a stratification change, but the idea that we're getting the same amount of carbonate, but we're switching over and having more and more foram carbonate was kind of a really interesting thought. This also means that the nanofossils are decreasing their contribution of carbonate to the bottom of the ocean. It's important to remind you now that the carbonate sort of buffering system capacity that the ocean has is one of the reasons that we have a stable sort of climate. It helps buffer the ocean against atmospheric CO2 changes, and it's a really important feature of the Earth climate system. So if we're switching the source of that carbonate, that could potentially be really interesting. Nanofossil and foram carbonate are different. So nanofossils are more resistant to dissolution, and forams are much less resistant to dissolution. So there's potential here to change the way that the ocean is buffering, which is potentially really, really neat. So Dan and Hannah had this thought, and we went and talked to Jamie Wilson and Andy Ridgewell, and we go, okay, so this might be nuts, but could you use Genie, and would this actually make a difference? And they went off and said, yes, that is doable. They used a new version of Genie that has a sediment modeling system to allow for looking at this kind of change in dissolution. They went off for a while, ran a couple model simulations, and then came back and went, well, nope. It doesn't make a difference really at all. If you use a similar kind of situation to what we found, you can change the atmospheric CO2 by about 5 per mil, actually 5.2. That is not a big difference. That means it's basically a negligible change, which is interesting, right? But also, Jamie kind of thought, okay, we could do better, right? Let's see what happens. What's the maximum change you can have? And so switched everything to aragonite, which is an even bigger change. And then switched, and then, so 0% calcite, all aragonite, and then went all the way the other way and all calcite, 0% aragonite. Biologically impossible. Just sort of trying to hit the system as hard as you possibly can, switch from one to the other, and you get about a 55 per mil change in CO2, atmospheric CO2. So really, again, not that big a deal. 55 per mil is parts per million is a substantial change when you're considering modern anthropogenic climate change. It's about 30 years of CO2, but it's still, in terms of that's as hard as a system can be hit, is not that big a deal, right? The biologically impossible switching kind of thing. So then I want to jump to talking about higher variation, higher frequency variation in size. So two master students had a couple of projects, and we wanted to look at what the even higher frequency variation in size could potentially be now that we had this much quicker imaging capability. So you're looking at the raw data for 4 different sites on the left. These span from the equatorial Atlantic up to sort of North Atlantic kind of latitudes. And on the right, you're looking at basically like a 5-point running mean. So you can actually see the information here, since it is pretty high frequency variability. So the record that we're going to be looking at is about 3 million years long. And so because size is generally driven by temperature, I was expecting the glacial interglacial cycles to pop out at us. So there's a 41,000 year cycle, and that happens about 2.5 all the way up to about 1.2 or so million years ago. And there's a switch, and we jump to a 100,000 year cycle. We call that switch the mid-Pleistocene transition. And so that's what I was expecting, right? Temperature dominated. That's the a priori expectation. If we look at that in a frequency space, we plot that information. The global climate looks like this. So these are precession, tilt, and eccentricity. And where you get a holiday color, we're getting that sort of frequency. And so here we're getting lots and lots of extended 41,000 year cyclicity all the way back here. And then we're getting eccentricity or the sort of the 100,000 year cycle right over here. So this is what I expected to get when I popped our information into that, and it's not what we got at all, which is, I think, potentially really interesting. So we've got a really strong 100,000 year cycle at most of these sites. Again, this is real data, and so there is an expectation that there's a lot more noise and you get more frequencies and harmonics and stuff. But what this shows is that there is a lot more 100,000 year cyclicity in the forams than you would expect, given the background of the climate and temperature. Interesting, this is also seen in nanofossils in some other work that's been done by a different group. So it's not just us. It seems like the carbonate system has this kind of frequency in it. And it's kind of weird. So to summarize those, we've got an unprecedented size change in the late Neogene that seems like it's important ecologically, but in the Earth system kind of framework, it's not that big a deal because it doesn't change CO2 nearly as much. But we can also see size is varying on orbital scales at sort of an important amplitude. And it also is weirdly operating independent of global, especially temperature drivers. So we need to think about that some more. All right, so the last thing I want to do is talk a little bit about the work that my group is going to start doing in the future. So I mentioned the sedimentary record when we were starting out, how these things are forming lots of carbonate on the bottom of the ocean. And then there's the evolutionary record, which there's a range chart on the right to sort of exemplify that. And there are people, including myself and others, who have looked at the connections between the sedimentary record and the evolutionary record even going so far as to compare the plankton foram and the sedimentary record itself. But one of the things that we've done is that we don't have as high quality data as we would like to investigate that sort of the correlations between those different records together and as great a detail as we'd like. And so, so again, because I'm me and I'm a micropaleontologist, like the answer to looking at how these two different records work together is, of course, the Joides resolution and IODP data. So the problem is if you look at IODP data and you try to get any sort of summative analysis and collect lots and lots of different sites data together, it looks like this, and it's horrible. This is LIMS. IODP Scientific Ocean Drilling has 3 different databases. They're all organized slightly differently. In the case of LIMS, even different expeditions have different headers for their spreadsheets. And so looking at this data together is really, really difficult. Age also doesn't really show up in these records very much. It's not one of the things that we have collected generally, except in certain situations historically. And so we're just sort of lacking in stratigraphy in these sorts of databases as well. And that's a big problem if you want to look at all the IODP records together. So there's a group of us that are using the paleobiology database and the macrostrat database to move IODP records and ocean drilling project records and deep sea drilling project records into the PBDB and macrostrat to better to increase accessibility and the utility of this information. So I've got several co-PIs. So there's Leo LeBay at Texas A&M and IODP. There's Jocelyn Sessa, who's at the Academy of Natural Sciences of Drexel University, and then Shannon Peters, who's at the University of Wisconsin. And we call our project the eoDP. We're very good with acronyms, apparently. We've been funded by EarthCube, which is an NSF project, basically using digital resources for geosciences. So what we're trying to do is take these existing tools and use them for scientific ocean drilling data. We are going to build some user interfaces that allow people to enter data and extract data. And then also we're trying to develop a productive and active user base through workshops and promoting our tools. The pandemic has made all of our workshops in person impossible, and so we're working on getting a virtual workshop series going. I'll have more information at the end. So the goal here is to take macrostrat and make it a sort of scaffolding where it's got stratigraphy and lithology, and it then serves that information to a variety of other sources, and you can mount other data onto it, right? Stratigraphy is the most important kind of data here. It allows us to view all this other information with the important historical context that it really needs. So all that's computer science, right? Databases and that kind of stuff. And it would be nice to actually tell you the useful things I'd like to do with it, right? Sort of the science side. So one of the things we don't do anymore is we don't map species habitats, right? And this is not, I'm not trying to be dismissive of work from a variety of people that have used geographic information to really great utility. But just looking at where species are back through time is something we haven't done since the 1970s. And even then it was really the recent because we didn't have good coverage back into the past. So the reason that's important actually jumps back to this that I showed in the beginning. All that macroevolutionary work that I showed and discussed has this geography built into it, but not acknowledged. So the records of our fossils really stink in places where they're not preserved, right? And we're biased here very heavily to an Atlantic kind of world or maybe an Indian Ocean kind of world, but we're missing the North Pacific and the South Pacific because we just don't have good coverage. And this probably exists persist back in time. And so we're probably biased in certain ways that we're just not acknowledging, and be useful to sort of tease out what's going on there. The other thing is that, and this is a really cool paper that Bridget Wade did in 2020. I will probably be chasing Bridget for my entire career, where she did a bunch of maps, which is, again, another thing we don't generally kind of do, but looking at the late Paleocene here, and then the PECM, and then the late Eocene, and there's this change, right? The PECM, you lose lots of carbonate, and then the late Eocene, you get it back. But also there's this, big radiolarian ooze tongue or some diatom oozes that show up right here and right there. And this paper, which was really neat, had some very basic conclusions that really argued against earlier things that we had considered to be sort of good paleoceanography before. Very counterintuitive kind of results showed up from this paper. And so just doing these basic kind of mapping things would be really, really useful. Both of these are graduate student projects that will be happening really soon. So I'd like to conclude by basically saying that we're moving, hopefully, toward a more holistic view of plankton evolution and sediment records. And then there are a couple of key scientific takeaways, right? Climate events are really important. We have important evolutionary inflections at these times. And that importance of climate really persists all the way down to the level of individual traits and sort of orbital scale frequency kind of controls. But one of the weird, counterintuitive for me conclusions is that it really doesn't matter who's growing carbonate. As long as we're growing the same amount of carbonate, it doesn't really seem to matter what kind it is at an Earth system kind of scale. One of the things we were worried about with that conclusion was that we were in a non-analog state, and that carbonate buffering was going to be different back in the past. And it's kind of a really optimistic conclusion that it doesn't matter who's doing it, that it just, as long as it's carbonate, we're good. And then lastly, if you're interested about eoDP, I would be happy to have you email me, and I'll put you on our email list so that you get included. The next thing we're doing is we're having a workshop sometime in the late winter, early spring about stratigraphy and large databases. So please drop me a line and I will include you on that email. And with that, I would like to acknowledge funders, NSF and NERC, and the University of Bristol, who I had a fellowship with for a bit, and then a variety of other people. So yeah, thank you very much.
Excellent. Thanks so much for that, Andy. This is really fun to hear about what you've been thinking about and all of the neat things that one can do when one tries to standardize microfossil diversity, ecology, and sedimentology, as one does. So just a general reminder to the audience that now we're entering the question and answer period of today's talk. So please feel free to send questions to the questions at eoPERCS host today. That is actually Chrissy. I was wrong earlier. So please send questions to questions at eoPERCS, and we will read them out for you. Or if you would like to ask Andy a question directly, feel free to use the raise hand button and we will call on you. And then just to get us going, I was wondering if you could talk a little bit more about standardizing sort of what is a species as you take that information into eoDP. So like, how do you define a species? And why?
Oh, simple questions, right?
I know, sorry.
Yeah. So as we're putting all of our data into the paleobiology database, the issue hasn't been how we're defining species. It's been cleaning up bad taxonomy or unrecognized taxonomy or simple misspelling. Dropping an I causes it to not be the same species anymore, right? And so there's been a lot of effort, especially from Jocelyn Sessa and Leo LeBay, cleaning up different microfossil records as we put all of this information in. I should say that a lot of that stuff has been solved also by the Neptune Sandbox folks, because they've got a good microfossil occurrence database as well. So theirs is more heavily curated. So it's a smaller subset of sites, but it's also really, really clean, good data. We've gone kind of the other way where we're taking everybody at their word and doing more of a PBDB style model where we take lots and lots of data and put it all in the system, arguing that the more data you have, the more secure you are in that the answer you eventually get is correct. But yeah, the sort of concern of morphospecies versus lineages, and then the fact that forams have morphospecies that are one genetic species is constantly a thorn in one's side. It's one of those intractable things, right? We can only do as well as we can with the data that we have. And so you kind of just have to do your best and try to consider that there might be a lot of extra stuff that you're including that isn't necessarily a true biological species, but is a morphospecies, and we're paleontologists, so that's what we have to use.
Very fair. All right. So our next question is related to that. What other morphological features besides size do you think might be valuable for tracking evolutionary response to environmental change?
Oh, yeah. So size is the easy one because it just jumps out at you. The paper that I did with Chris that was about the recovery from the late Cretaceous had, I think it was 34 or 38 different measurements that we compressed down to sort of mid-20s kind of morphological parameters. And this included like the rate of chamber expansion, so how quickly, how quickly the different chambers grew. There was some like what the position of the aperture was relative to the coiling direction. And so there's a variety of different parameters. It's just the reproducibility of those can get really tough because these things are so small. Even just orienting the foram on a slide is really tricky. And I've spent long hours poking individual sand grain sized fossils, trying to get them to just right orientation to really take a good measurement. So yeah, it's like doing morphometrics on an invert fossil, but only really tiny. So you have to use a paintbrush to like poke it. But one of the things with forams is that we're not entirely sure the significance of the test, and we don't always have a good idea of the functional significance of these traits. And we're using them, but we're not always sure that there is a functional significance attached to them. It seems like there probably is. We know that some traits like spines have functional significance, but there's a variety of different parameters, but choosing the right ones that are reproducible can be tough.
I definitely feel your pain with the trying to orient the teeny tiny fossils just right with the paintbrush, and I just gave up. So yeah, you're better than I am.
I knew you would feel that way.
Morphospecies and discrete characters. Anyway, moving on. The next question is excellent talk. Thanks. Do the 100,000 kiloyear or 100 kiloyear variations in foram size show the amplitude modulations of eccentricity, e.g., 4,000 or 400 kiloyear and longer?
I have not looked at that yet. I don't think that our records are long enough we'd be able to confidently say for sure, because they're pretty short records, because the master students in the UK don't have a ton of time. It's like 6 months to do a research project and write it up. So we don't have a huge long record of like many multiple millions of years. And there is quite a bit of variability. So I'm not positive. It's the kind of thing you could sketch out by eye, but I don't think we could be rigorous about whether or not that was apparent or not. It's a really good question, though.
Great, thanks. So our next question is a little bit more speculative. It says, if you could acquire data where there are sampling gaps, where in time and where in the world would you go and why? I feel like EODP is trying to hit all of the world. But
yeah, so honestly, if there is an undergrad that wants to do a master's project, one of the master's projects I want to do, please don't anyone take this idea, is to use eoDP and Neptune and sort of combine a bunch of different microfossil databases together and look going back through time at where information is lost and where the geographic information is lost, where and when that happens. So looking at how robust the microfossil record is, and where we lose geographic coverage and how that happens, sort of basically testing, do forams and other microfossils have the best fossil record? Actually giving that a rigorous test. Now, that project I want to do, because I don't know how to answer that question, basically. It's probably the Pacific, it's probably the South Pacific, which is why historically IODP doesn't go there, because IODP loves carbonate when it comes to paleostratigraphic studies, because that's where we've got good biostratigraphic, except for Elizabeth's stuff, controls and geochemistry and all that kind of stuff. And so that's why we avoid the South Pacific like it's the plague. Sorry, that was a bad metaphor. But basically, I think that's probably where. And also, the Cretaceous is kind of this, we've got a couple of spots where we've got coverage, but other than that, we're really limited, which is why we generally, when we're talking about the evolution of microfossil groups, we generally focus on the Cenozoic, because the Cretaceous is we acknowledge it's much weaker. So I guess the answer is probably the Pacific, not equatorial regions in the Cretaceous, I guess.
I know IODP needs to get on those red clays. So at this point, we don't actually have any additional questions. So I'm going to remind the audience, if you do have a burning question for Andy, we'll give you a moment to get it back in. And while we're giving you a moment for our last call for questions, I was just curious from an imaging standpoint of how you could actually process and prep 70 to 100 samples per day for this imaging scope, if you still have to make sure that the forams aren't touching, for example. How do you do that?
Yeah, so we spread it out on a tray that's larger than a standard picking tray, and it's glass with a flat, like a velvety kind of black background underneath. And so you just spread out and you try to do about 2,000 specimens, which actually, because it's a much larger space, is actually kind of doable. The computer, because of the thresholding sort of settings that allow us to look at just the forams, will also throw out forams that are touching. And so as long as we're getting 2,000, over plus the ones that are touching, you're actually okay.
Gotcha.
The throughput problem is washing, and because that takes a lot longer than imaging at this point, which is a complete flip to the way it used to be. Yeah. I mean, the computer runs pretty smoothly and quickly when it's not broken, because the software kind of stinks. But yeah, it was a pretty sweet, nice setup when it was working like I wanted it to.
I feel that. I feel like Andy and I are just going to have a conversation about high resolution, high throughput imaging for the rest of our careers. But I will not follow this up. We did actually have another question come in during this interval. So perhaps this is your last question for the day. Is the resolution of the geological maps available on Microstrat is highly variable with geography? Is this something that you have a solution for?
So it's very... Yeah, so I think that is variable because the underlying data is highly variable as well. So it depends on, if you're looking at sort of the North American maps, then it has to do with how far apart the Kosuna charts are, which was the original data that Shannon was using to build those. And so the underlying information is going to be the IODP data. And so it will change, and it'll get much, much lower as we go back in the past, because we just won't have as many sites to connect to. One of the things that's going to be really tricky is because we're looking in the ocean, water depth of the site is going to be really important. And so instead of having 2 dimensions to care about, we're going to have 3 dimensions because of the symmetry to care about as well. And so that'll increase the complexity of the project and the analyses that need to happen quite a bit. So I'm less concerned about geography I'm interested in geography, but I'm more concerned and worried about the symmetry, I guess. Keeps me up at night.
Sounds like the stuff that nightmares are made of or something. All right. So at this point, I'd like to thank Andy for an excellent talk and a great job fielding all of those questions. And we'll just go ahead and do our little closeout. So we'd like to thank Andy for his talk, and also all of you for joining us today for eoPERCS. And we'd like to remind you to please fill out the weekly feedback form, which we'll drop in the chat shortly. And also feel free to nominate anyone you think might give a really good eoPERCS talk. We'd love to hear about all the early career researchers out there, because we can't possibly find them all on our own, but we do keep trying. And speaking of excellent early career researchers, we're really excited that next week is going to be our last seminar of 2021. And rather than having an official seminar, we're actually going to host a panel discussion with a number of returning eoPERCS seminar speakers, discussing their experiences with grad school and navigating grad school in a very wide diversity of locations and communities and universities. And so we really encourage you to join us for that discussion and that panel. And I hope that this will not be our first and only paleo panel. So we also have, my computer just went blank. I'm sorry. Jenna, I think you're going to have to start talking.
Hi, thanks, Elizabeth. So yeah, next up, we have tea time with Andy. So stick around if you can. This is just an informal conversation where we can talk in a relaxed setting about anything that interests you about the talk or his work in a really broad sense. The question of the week is, would you rather be a planktic foraminifera or a benthic foraminifera? And that can get quite heated. So stay tuned. Yeah, and so before tea time, we're just going to take a little break, get up and walk around for a couple minutes, get something to drink, bring your pets if you have them. We always love to see everybody's pets. So I'm just going to start the timer, and we'll see you all for tea in 2 minutes.